Hi there! Welcome to a new physics lesson filled with adventure and discovery. Today our topic is electric field. We looked at electric force last time and electric charge, and today we're kind of bringing them all together to talk about electric field. We're going to look at how to calculate for the electric field, we're going to look at how to draw electric field lines, and then we're also going to look at what does electric charge look like on conductors, such as metals that can conduct electricity really well. So that's our topic for today. Thanks for joining us, and let's jump into it. So first of all, field forces. When we talk about electric field, we have to discuss field forces. Whenever there's a given area or there's a given space that there's an exertion of force on that space, we have what we call field force. So for example, as you sit there in that chair watching this video, gravity is being applied to you. Gravity is pulling you downwards no matter where you are in this room. And so this room here is what we call field force, or gravity is what we call field force. It's exerting its force on this area. And so a field force is a force that exerts its energy and pulls or pushes you without actually touching you. So gravity is a good example of that, and also electric force is a good example of that. And so for electric fields, every time you have an object with a certain amount of charge, it's always going to create an electric field around itself. Whether it's a proton, an electron, or something really big with a lot of electricity, it's going to cause a field around it. And so if we bring another charge into that field, then it will cause, depending on if it's positive or negative, it's going to it's going to push or pull it. It's going to force it. And so we use this simple equation to calculate for electric field. And notice that it's on the top of your equation sheet. Yours is a little bit different. Yours says F electric over Q, what we call naught, or Q0, which Q0 is a test charge. And so interestingly enough, the only way we can test the electric field is by sending what we call a test charge into it and observing what happens to that point charge. And so we have a second equation we could also use if we don't have the force of the electric field or the electric charge. We can use this equation instead to figure out the electric field. So notice, and just to go over this, E is electric field, F is electric force, Q is that test charge, like I said earlier. And this one is a little bit different. We have the point charge here, electric charge here. We have the K, which is Coulomb's constant that we were using last class. And then we also have the radius, the distance between those two objects in meters. Okay, so we can use this to calculate our electric field. Now what's also really important is electric field lines. And so we can use arrows to give the direction as well as the quantity of the electric field. And so like I said earlier, we can find out the electric field by placing what we call a test charge or imaginary positive charge. Because if that positive charge is repelled, that means our electric field, we have some kind of positive electric field. And if if it gets attracted, that means we have a negative electric field. So let's say we didn't know what the charge is of this red area here. It's positive because I put positives there. But let's say you didn't know. If we put a test charge there and it got repelled, okay, if it moved away from that electric field, we know that there's a positive electric field there. And vice versa. If we have a negative electric field and our electric charge is drawn towards it, okay, that means that it's a negative electric field. And so notice that because it's a positive charge that's being attracted to it or a positive charge being repelled to it, we draw arrows to represent that motion or the direction of this electric field. And remember, it's based upon a positive test charge, okay, a positive test charge. So because there's a positive test charge here, these arrows move away. This is going to move in the same direction as a positive test charge, if that makes sense. So because a positive test charge would move away, we would draw the arrows away from the field. And vice versa, if we have an electric field, a negative electric field, we draw arrows towards it, which is the same direction as a positive test charge would if we put it next to it. And so positive versus negative electric charge, if you have a positive charge, notice that we're going to draw the electric field lines away from the object. And then if we have a negative electric charge, our field lines are going to move towards it. Okay, so field lines go away from positive charges and they go towards negative charges. And it's all because we usually use a positive test charge to test electric field. So here's the rules for drawing field lines. The lines always have to begin at the positive charge. Okay, so they always begin at the positive charge and they always end at the negative charge, or what we call infinity. Okay, so they always begin positive or infinity and end negative or infinity. The number of lines are proportional to the magnitude of the charge. So if I have a lot of lines, so if I were to count all these lines, I could calculate the charge of this field, or this point. So let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16, positive 16 charge here, and I'm going to assume that we have the same here, negative 16 here. Okay, so the number of lines are proportional to the number of the charge. So the more lines I have, the bigger the number, the bigger charge I have. Field lines can never intersect each other. They're always going to move parallel to each other, and the closer the lines are, the stronger the forces at that certain point. So let's take these two examples. So notice we have two equal but opposite charges where I have 1, 2, 3, 4, 5, 6, 7 field lines going between them, and each one has 1, 2, 3, 4, 5. Each of them has 12. Okay, so each of them has 12 lines either going towards or away from each other. So they're equal. They both have a charge of 12. And so notice the lines go from positive to negative. None of them intersect. And the closer they are together, so right here would be the strongest electric force. Okay, so I'm going to move this up here. And then on the opposite hand, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, these charges are equal also. They're both positive. They both have a positive 9 charge, and they're going to repel each other. Okay, and then, like I said, electric field is the strongest where the lines are the closest. So between here is pretty weak. This is a little bit stronger, and then this is the strongest. On this side, this field strength is the strongest right here, and then it gets weaker as you go towards the center. Okay, so pretty cool. Electric field lines are pretty cool. But moving on to our last topic, the charge on a surface conductor. A conductor, just as a review, is an object that is able to transfer electricity, or to transmit electricity. And so what's interesting about conductors is that you'd think that the charge moves all the way through the conductor. Right, so like metals are really good conductors. So we use metal wires to conduct electricity, and you'd think that it moves all the way through. But the interesting thing is that we find that the charges on the conductor are actually all on the surface of the conductor. And the reason for this is because since the electrons are the things that transfer the charge in a conductor and a metal, and so that's why metals are really good conductors, is because they have all these loose electrons all over the place. And so because they have all these loose electrons, all these electrons repel each other, and they move as far away as they can possible, which is the surface of the conductor. And so because of that, the farthest that they can possibly go is the surface of whatever wire conductor that we have. There's actually no charge inside of the conductor. They're all just lining up and end up on the surface of the conductor. And so what we can say then is that since it's evenly distributed on the surface, all the field lines on the inside of the conductor actually cancel out each other because of all these negative charges. They all repel each other. They all cancel each other out. So inside of the conductor, okay, so we have this pink charge conductor and all the charges this green area. The electric field inside of this conductor would actually be 0. Okay, E is equal to 0 inside of the conductor. All the charges on the surface and none inside the conductor, so there is no electric field inside of the conductor, which is kind of interesting to think about. Okay, so that's electric field, and so thank you so much for joining us, and we'll see you next time.